Welcome to week 2 of the ma161 calculus. My name is Kurt Pfeiffer and this video is about functions. Functions are the bread and butter of calculus, and that's what the rest of this course will be about. Functions are used by scientists to model real-world phenomena and develop theories about the real world. We've all been experiencing an increase in the use of function language, calculus language even recently, when people talk about exponential growth or flattening the curve. That's all a sign of the fact that scientists try to come to grips with an unknown virus in terms of models that use calculus functions. It's not really a surprise, because functions arise whenever one quantity depends on another. Here I have a simple example. I have a collection of circles, and obviously I have the radius of the circle here marked as a red line, and obviously the larger the radius of the circle, the larger the area will be. That describes a dependency of the area on the radius of the circle. And the area, called capital A in what follows, of a circle depends on the radius, called little r. The equation A equals pi times r squared makes that dependency more precise. It shows that the area grows with the square of the radius, and there's the circle number pi involved. This gives a formula, gives a precise rule that connects r and a, that allows us to compute a from any given r. This formula assigns to each positive value r one precise value for the area A. Here in the calculus we say that A is a function of r, and write A of r is pi times r squared. In such a setting, the A is called the dependent variable and r is called the independent variable. A depends on r. Functions are used as mathematical models. A mathematical model here is a mathematical description by means of a function or an equation of a real-world phenomenon. The purpose of the model is to help understanding the phenomenon and perhaps to make predictions about future behavior. Here's a little sketch of how things relate. Down here we have the real world, and up here we have the maths level. In the real world, there's a problem to be considered by a scientist. Scientists formulates a mathematical model in the form of an equation or function of the problem. Then they apply the calculus to solve the problem in calculus terms and come to a mathematical conclusion. This conclusion then is translated back or interpreted in the real world setting, and there possibly makes a prediction how this real world setting will behave in the future. Now the real behavior of the real world thing can be tested against the prediction that comes from the mathematical model, and depending on the outcome of the test, the model needs to be refined or whatever. A good model simplifies reality in order to permit mathematical calculations, while on the other hand it needs to be sufficiently accurate to provide conclusions that are valuable. This has been stated as everything should be made as simple as possible but not simpler, a quote that's often attributed to Albert Einstein, but lots of other people have come to that conclusion. Among scientists, this principle is known as Occam's razor, or the law of parsimony, and dates back to the 14th century. Simplification happens when reality is modeled through functions, and it's important to be aware of the limitations of the chosen model that result from these simplifications. Let's be a bit more precise and introduce some notation, language around functions and how they are used in this course, in the calculus. We define a function as a rule that assigns to each element x in a set capital X exactly one element called f of x in a set capital Y. And that is, a function is built on two sets, a set x of inputs and a set capital Y of outputs, and it acts as a rule or a machine that takes a little x, an element little x from the set capital X, and turns it into an element y of the set capital Y, which is called f of x, the f of x. The x is always turned into the same little y, into a unique value. We write this as f colon x arrow y, and that describes f as a function from x to y, where both x and y are sets. The set x here is called the domain of the function f. The element f of x is called the value of f at x, or the image of x under the function f, and it's pronounced as f of x. There's another set of importance in this context, and that's the range of the function f. The range of the function f is the set of all these elements f of x. All the values f of x which lie in the y set that do occur as x varies over the domain. In the calculus, both x and y are usually sets of numbers. And you can see a certain difference between the roles that are played by x and y. The function f will use every element x in the x set, and it'll assign to each x a unique value f of x in the y set. That doesn't mean that every element y in the y set does actually occur as a value, and it is also possible that a given element y occurs repeatedly as a value f of x for several elements x in the x set. We'll see examples of functions now where we see all these concepts in action. So we start with a short list of examples of functions. And there's one function around, it's the age of the students in this class. It's a function from the class, here x is a set of students, to the natural numbers, the y set is the set of natural numbers, and it assigns to each student the natural number which is their age. That's a function from the set of students to the natural numbers. The second example on my list is world population as a function of time. World population p of t at any given time t can be regarded as a function from the real numbers. The domain x is the real numbers representing time, to a set y, which is again the real numbers used to measure population size. The third example is a list which I found on the Wikipedia. It's a list of years in which city status has been legally recognized to the cities in Ireland, starting with Dublin in 1172, Cork 1185, Limerick 1199, Waterford 1202, and last on the list is Galway 1985. The fourth example consists of a list of 4 functions here represented as graphs in the xy plane. I won't discuss the details of these now. Maybe just point out that the last one on the list here, that's exponential growth. Starting off slowly, barely recognizable, and then it takes off suddenly and disappears, growing faster and faster. Number 5 is a so-called quadratic function given by a formula. F of x is 2x squared minus 3x plus 5. This formula describes a function from the real numbers to the real numbers. And finally, one of my favorites, the identity function. F of x is x. Output equals input. It's a function that has domain and range, all of the real numbers, and we'll meet that function again in a particular setting later in the course. What these examples illustrate is that there are many ways to represent a function. Actually, we can distinguish 4 ways in which functions can be described. First, they can be described verbally, that is, by a description in words. And that's how I described the age function on the previous slide. Secondly, they can be described numerically, as a table, listing all the values explicitly. That's what the table of city status recognized does on the previous slide. Or we can represent a function visually by its graph in the xy plane, and we've seen a few examples of that on the previous slide. And the fourth popular way to represent a function is by a formula. We can call this the algebraic way to represent a function. Potentially, any given function can be represented in all these 4 ways. And it's often possible with ease and actually useful to go from one representation to another form. Here's an example, a typical word problem as you might find it in textbooks or on exams. Here it's about a rectangular storage container with an open top that has a volume of 10 cubic meters. Its base is twice as long as it's wide. Material for the base costs €10 per square meter. Material for the side costs €6 per square meter. The task is to express the cost of materials as a function of the width of the base. A word problem typically asks us to convert a verbal description of a function into an explicit algebraic formula, so that we can work with that and compute things, maximize things. I won't do that now. And the example is here to illustrate how it makes sense to move from one type of description of a function to another. Here's a tabular representation of a function. Sometimes these tables are useful, for example log tables. This table here we use in grading sometimes, where we convert a percentage grade into an exam grade, and how to do that is specified by an explicit formula. Where it says that percentages between 70 and 100 give a grade A, between 60 and 69 give a grade B, and so on. The domain of this function is the set of all the possible percentages, that's integers between 0 and 100, and the range of this function is the set of possible grades, these ABCDs possibly decorated with plus or minus. That's a tabular representation of a function, and this particular one raises the question, is there any other, better, more useful way to represent that information? I don't know. Graphical representations we'll see quite often. A common way to visualize a function from a set x into the real numbers is its graph. That's the set of all pairs of x's and y's, where x is in the domain, x, capital X, and y is the function value, f of x. That's a collection of points, which is specified by the function, and it lives in r squared, the xy plane. Now here's a typical graph. We have the x-axis going from here to there, pointing to the right. We have the y-axis from here to there, pointing upwards. We have a few labels on the axis. On the x-axis has 2, 4, 6, minus 2, minus 4, minus 6 labeled. The y-axis we have 10, 20 and 30. These scales are chosen as they fit, in a way to make this graph useful. And we can use the graph to read off properties of the function. For example, we can tabulate values, if that's what we're interested in. Now we can read off values from the graph and put them in a table. Here we find at x equal to minus 4, we find a y value which is around here, possibly 24, minus 2. The x value minus 2 in the graph corresponds to this point here, and that corresponds to the y equals 10. F of 0 is 4, f of 2 is 6, f of 4 is somewhere between 10 and 20, 16. That's one way to use the graph. We'll use the graph in other ways as we go along. The graphical representation of a function is quite useful, and often we'll be asked to go from a formula representation to the graphical representation. Sketch the graph. Now it's typical that a function is given by a formula. Here is an example of a function given by the formula 2x cubed minus 1. It's a function from the reals to the reals. And we can, for example, compute and tabulate some values, if that's what we're interested in. We can compute the function value at 0 by substituting 0 for x in the formula, and we get minus 1. Substituting 1 for x in the formula, we get 2 minus 1, which is 1. Substituting 10, we get f of 10 is 1999. F of minus 1 comes out as minus 3. F of minus 10 we can compute as 2 times 1000, minus 2001, and so on, as we like. The formula for the function can also be used to sketch its graph. This function, f of x, given by the formula 2x cubed minus 1, obviously has domain R. That's how we set it up here in the beginning. The range of this function, the set of all values f of x that do actually occur, is also all of R. Or is it? We will develop tools as we go along to answer such a question definitely and accurately. For now, I just want to raise the question. Same question can be raised for the domain. Like, often a function is just described by a formula without stating the domain explicitly. That raises the question, what is the domain of this function if it's not stated explicitly? We will use the following convention in such circumstances. We say that the domain of a function, if it's not explicitly stated, is the set of all numbers x for which f of x makes sense and gives a real number output. To illustrate this further, I've brought two examples. First example, find the domain of the function g of x given by the formula 1 over x squared minus x. At first glance, that's a perfectly valid formula, so what could go wrong? Where would the function value not make sense? Well, if you try out a few values, if you substitute, for example, 1 for x in this formula, you'll end up with 1 divided by 1 squared minus 1, that's 1 divided by 0. And of course we must not divide by 0. Now this function doesn't work, doesn't make sense at x equal to 1. Actually the same thing happens when you substitute 0 for x here, and then it's 1 divided by 0 minus 0. It's still 1 divided by 0, which we must not do, which doesn't make sense. And we can, by factorizing this denominator, x squared minus x, as x times x minus 1, we see that this denominator becomes 0 exactly when x is 1 or x is 0. These two choices for x cause a division by 0, which we must not do. So this function g of x is not defined at x equals to 0 and x equal to 1. So its domain is all the real numbers x that are different from 0 and different from 1, a set that can be specified in interval language as the union of three intervals: the interval from minus infinity to 0, the open interval from 0 to 1, and the open interval from 1 to infinity. The second example is concerned with the domain D of the function square root of x plus 2. Square roots are only real if you take the square root of a non-negative number. Square root of x is not a real number if x is negative. So here we must take care that x plus 2 isn't negative, and we find that the domain of this function, the set of real numbers where this formula square root of x plus 2 gives a real number output, is the set of all real numbers x which are greater or equal minus 2, which in interval language is the interval from minus 2 to infinity, including the minus 2 on the left hand side. Not every equation, table or graph defines a function. So how do we recognize? How do we recognize which does define a function? Here is a table relating values of x to values of y. 2 related to 3, 4 related to 3, 5 related to 2, 5 related to 7, and 6 related to 6. If you read through this table, you'll notice that there's some repetition, like the number 3 occurs here and there, twice in the y row. The number 5 occurs twice here in the x row, and the number 6 occurs twice here in the last column. What causes a problem in terms of reading this table as a function that assigns to each x a unique value of y is the fact that the number 5 occurs twice here, because this leads to here assigning the number 2 to 5, and here we assign the number 7 to 5. Which is which? This table does not define a function because the x value 5 here is used for two different y values. This phenomenon can be described in geometric terms as the so-called vertical line test. When your function is given as a curve in the plane, or when your x and y values are given as a curve in the plane, then one can decide whether the resulting graph is the graph of a function by applying the vertical line test. And the vertical line test says a curve in the xy plane, any curve in the xy plane, is the graph of a function f of x if and only if any vertical line intersects the curve at most once. And that's the geometric formulation of what we saw is violated in the table up here. The vertical line through x equal to 5 in this table, so to speak, intersects the curve at the y value 2 and at the y value 7. This is better seen in an actual geometric setting. Here I've brought a few examples. Maybe the prototypical example of a curve that's not the graph of the function, despite being very nice, is that of a circle. Here I have the circle of radius 3 around the origin of the xy plane. A circle, a curve that is described by a formula being x squared plus y squared equals 3, but it's not the graph of a function. And the vertical line test here, applied in the form of this red line, indicates that this vertical line here does indeed intersect the blue curve twice. It's once here and once there. This curve is not the graph of a function. In contrast, the next curve looks like a parabola, and in fact it is. It's the curve described by the equation y plus 3 equals x squared. Here, and I've only indicated one vertical line in green, and this is a vertical line which intersects the blue curve exactly once. And you can see that wherever I place this green line as a vertical line on this graph, it will always intersect this blue line in exactly one point. And the requirement is that it intersects the curve at most once. So this parabola is in fact the graph of a function. Next example here is a parabola lying on its side. It's again a curve that can be easily described by a formula. The formula here would be y squared equals x plus 3, for example. But being a parabola lying on its side with its two arms, if you draw a vertical line here, a red vertical line through this parabola, you get two intersection points. This curve is not the graph of a function. However, if we get rid of one half of it and only look at the, say, positive part of the curve, then we're looking at the curve which can be described by the formula y is the square root of x plus 3. And this now again is a curve where any vertical line, and here I have one green line drawn, any vertical line will intersect this curve at most once. So this curve is the graph of a function. That's the basic setup, function language, and what properties a function should have, how it can be represented in the different ways. The next video will be about properties of functions. And just to finish up here, the vertical line test expresses exactly how we set up a function earlier in this video. Namely, we said that the function is a rule that assigns to each x in the x set exactly one value of the y set. That's what the vertical line test here expresses in geometrical terms. See you in the next video.